All right, so I guess we'll continue then with what we were working on last time. There's one topic we didn't have time to get to that I do want to finish discussing from last time, because it is important to some of the issues we'll talk about today, and that's the topic of step size selection. So we were talking about numerical integration and various numerical integration schemes, and one of the things that often comes up in these schemes is that we will have some numerical integration step size, something of the form delta t, and we'll want to pick the appropriate delta t. Now, if we really go through in detail the kinds of error analyses we went through last time, you can figure out some very specific guidance for what delta t should be. So if we were using, for example, the forward Euler method, that's something we analyze by looking at a Taylor expansion of the term x of t plus delta t, and we could say that that comes out to x of t plus delta t x prime of t, which is the forward Euler iterator, plus an order delta t squared term. And if we want to be more specific using the truncated Taylor series, the delta t squared term has the form delta t squared over 2 x double prime of some unknown psi between t and t plus delta t. And we can use that, if we really want to try to put a more explicit bound on what step size would be appropriate for a given problem. So, for example, if we're trying to simulate a total amount of time tau, and we have some error bound epsilon that we're trying to meet in that time, then let's say we look at this and we're able to put some bound on the second derivative. So we can say that x double prime of psi within whatever region we're looking at can't be more than some constant c. Then we can be very explicit about what delta t is good enough to give us our desired error bound for a desired amount of simulation time. So if we are trying to simulate a time t, then we have tau over delta t steps of integration that we want to do. And we can say from this error analysis that the error per term is going to be bounded by c over 2 times delta t squared. And we're trying to assert that this is less than some error bound epsilon. Then we can just solve for delta t, and we're going to end up getting the conclusion that delta t has to be less than 2 epsilon over tau times c. So we could get a very explicit formula, and you could do the same thing for a higher order method. So if we had one of the higher order methods, we'd get an error term that would look something like, let's say, delta t cubed over 3 factorial times the third derivative of x. But basically, we can get some form and we can put an explicit bound on the delta t we want. In practice, though, that's not usually what you want to do. So the reason for this is that the characteristics of a problem can vary quite a bit among different regions of the problem. So it might be that we're trying to numerically integrate a system that has kind of interesting, complicated dynamics early on, but then kind of settles into some smooth, steady state. And the step size we want here in this complicated region may be very different than the step size we want here in this smoother region. Once it smooths out, the second derivative gets very small, so we can get away with a big step size, whereas here you've got big second derivatives, you need a tiny step size. And if we're looking at a simulation where we're spending a lot more time in the smooth domain, you don't want the worst possible part of the worst possible region of your integration domain to dictate the step size you use in the entire region of the simulation. So because of that, what we often do is use what are called adaptive methods. And adaptive methods are sort of similar to what we had seen when we looked at numerical optimization with respect to, let's say, the Levenberg-Marquardt method, where we're trying to create a method that can find an optimum for some continuous function, and we adjust the step size, the amount of steps we're taking, or the distance each step takes, to try to use a small step when we're in very bumpy regions or optimization, a big step in smoother regions. And you basically want to do the same thing with numerical integration, typically. So does this make sense to everyone? Okay, so there are a couple of ways we can do this. The simplest one is to do something like the following. we can say that we've got, let's say, a forward Euler iterator we're trying to simulate. So we simulate a forward Euler step. And then we try to test the accuracy of that by using a more accurate approximation. And the simplest way to do that is just shrink your step size and try again. So we could say that maybe we've got some x hat of n plus 1/2, which will be half of a forward Euler step, sort of like we're doing the midpoint method. So that is xn plus 1/2 is xn plus a half time step delta t over 2, f of xn. And then just do, instead of doing what we do with the midpoint method, just take one more full step. So we get xn equals xn plus 1/2, excuse me, xn hat plus 1/2 plus delta t over 2, f of x hat n plus 1/2. So what we're doing is just running forward Euler again, but now running it with half the step size. So what should that do to the error relative to the full step size? How should the error in this approximation compare to the error in this approximation? Yeah, forward Euler has a first order error, so we would expect that if you shrink the step size by half, you approximately cut the error in half. That's not really exact because there's a lot of approximation and constants that go into that, but roughly speaking, if you do a forward Euler step with half the step size, you should get about half the error. And the simplest version of an adaptive method is just to try two different step sizes, compare the approximations, and use the distance between them as roughly an estimate of how big the error was in the original approximation. So roughly speaking, the error in this approximation should be about twice the distance between these two approximations. And you can use that to figure out on any given step if you're using more error than you can get away with. So if we're trying to bound our total error by epsilon, we say that maybe if we're taking tau over delta t steps and we want total error epsilon, then we'll allow epsilon delta t over tau error per step. And then we can just use this estimate to see if we're getting too much error on that step. And if we are, then we shrink delta t and try again. So that's the simplest version of an adaptive method. So does that make sense to everyone? Right, so you can improve on this a little bit by using something called an embedded method. And an embedded method is something that would start more or less the same way as what we had seen here. So you could do, let's say, a forward Euler step. But then what we're going to do is do something that looks like the following. We're going to say that x hat sub n is equal to x sub n plus delta t over 2. And instead of doing delta t f of x sub n, what we're going to do is f of x sub n plus f of x sub n plus 1. So in other words, we run a forward Euler step, we get an estimate of the value at the other endpoint of our interval. So we're at t, let's say, we're trying to get to t plus delta t. We estimate the derivative here, we estimate the value of the point here, given that derivative estimate, then we estimate a new derivative, and then we kind of average them to get an idea of what the derivative actually is, and then use that to estimate what the value of our point is. And although it may not be obvious, what this is going to do is actually give you a second order accurate approximation. And the reason this is called an embedded method is that the work we did getting our first order accurate approximation helps us get our second order accurate approximation. So we do work to get a forward Euler approximation, and then we do basically the same amount of additional work to get the second order approximation because we already got this in getting the first approximation. We already know this, we already know this. So an embedded method is just a more efficient way of getting two approximations where basically you're getting a higher order accuracy approximation sort of for the cost of a low order accuracy one because you've already got this low order accuracy approximation that you can use in getting your higher order accurate one. So does that make sense to everyone? Okay, so this is more commonly what's done when we work with embedded, or when we work with adaptive step sizes. And there are lots of adaptive schemes that have been worked out. So there are Runge-Kutta 3-4 schemes and Runge-Kutta 4-5 schemes, where basically for the cost of just a fourth order Runge-Kutta, you get a fourth order and a third order approximation, or for the cost of a fifth order Runge-Kutta, you get a fifth and a fourth order approximation, and then you just compare those two approximations to figure out if you need to shrink your step size. So that's basically how this usually works. And if any of you use MATLAB for numerical integration, these kinds of routines are built in. It's like there's a routine called RK45, which is doing exactly this thing. You can do this kind of adaptive method with multi-step methods as well, so things like the leapfrog method, but it's much more complicated because generally, if you're trying to do something like a multi-step method where the value at a new point depends on the value at several prior points, if you keep changing the size of the steps between those points, you're kind of messing up your whole scheme. It's very hard to do that correctly and not get bad stability properties or bad accuracy or something like that. But there are schemes where this has been worked out that are known as predictor-corrector methods. And I'm not going to go through those in this class, but just be aware those are available. You can do multi-step numerical integration also with adaptive step sizes. Just it's easier to do it with single-step methods. So any questions about any of that? Okay, well then we can move on to the main thing I wanted to talk about today, and that is moving to the consideration of systems of multiple dependent variables. Or excuse me, multiple independent variables. So we saw in last class, for the most part, numerical integration of systems of the form x of t, where we would generally know the derivative of x with respect to t. We would have some way of evaluating that. We're trying to integrate a single independent or a single dependent variable x given a single independent variable t. We saw that it's pretty easy to generalize to the situation where x is a vector. So we have multiple independent variables, or multiple dependent variables, but a single independent variable. But today what we're going to look at is the situation where we are going to consider that we could have multiple dependent variables and multiple independent variables. So, for example, we might have several variables that we're trying to evaluate, and these themselves are functions of several variables. So this isn't as simple as generalizing from a single dependent to multiple dependent variables. But we can see how to do this by considering an example system where this comes up, and the example system I'll give is the following. Let's suppose we are looking at some chemical solution, and we're going to imagine that we put a barrier between two sides of, let's say, a beaker of solution. And in one side of the barrier, we've got a very high concentration, and on the other side, we have a low concentration. And the thing we want to simulate is, if we take out the barrier, what happens? So that would be an example of a system with multiple dependent or independent variables. So what are the independent variables in this situation? Well, if we're trying to simulate a system like this, one of the independent variables is going to be time. We're asking what happens when we take out this barrier, so what's happening over time.
Volumes on either side of the barrier?
Yeah, so we have additional independent variables that correspond to spatial dimensions. So what happens in this system is going to be different close to the barrier than far from the barrier, so we need to keep track of space. So in a system like this, it might be that our independent variables are x, y, z, and t. So that would be an example of a system where we're trying to study time evolution of something that has both spatial and a time dimension. So is that clear to everyone? Okay, so that's the system we're going to set up. And what will often come up in these situations is that the behavior of a system like this is described by partial differential equations, or PDEs. And that's what occurs in this case, that if we start with some initial conditions, we start with some initial set of concentrations, the time evolution of this system is actually described by the partial differential equation d, let's say c, we'll use as the variable for concentration, dt, and here we're using partial derivatives, is equal to some diffusion constant times the sum of the second partial derivatives of c with respect to the spatial dimensions. So d squared c dx squared plus d squared c dy squared plus d squared c dz squared. And this is often abbreviated as dc dt is equal to d times this triangle operator, which is referred to as a Laplacian. So this triangle squared is a Laplacian of c. And this Laplacian just means the sum of the second partial derivatives with respect to space. So basically what we're going to be looking at today is how we would simulate a system like this, where we're doing partial derivatives with respect to multiple independent variables. Right, so any questions about that? So I should point out that the particular equation I just wrote down there is a general equation you use to simulate diffusive systems. It's actually known as the heat equation because it's the equation originally formulated for understanding the diffusion of heat in some kind of solid, but it also is relevant to chemical diffusion or other kinds of diffusion processes. So to see how we're going to solve that, I'm going to start by making things a little simpler and assume that we're looking at this kind of system in basically one spatial dimension. So assume that we've got some kind of thin capillary that has an x dimension, but we'll assume that the y and z dimensions are basically 0. So we're really going to be looking at a system where we're trying to study the evolution of c with respect to x and t. And if we want to do that, the basic idea behind how we do it is not too different from what you do to simulate evolution of a system with respect to time. What we're going to do is discretize. So we saw previously that we would discretize time into units of delta t, and we're going to do the same thing with respect to space. We're going to break this region into units of some size delta x. We're going to think of this as a set of discrete points spaced delta x apart within whatever region we're looking at. And that'll give us a way of coming up with an explicit statement of what we want to solve here. Right, so if we want to do that, what we can sort of say then is that we can think of each of these points in space as its own independent variable. So we derivative of c at spatial point 0 with respect to t, and we know that that's given by the second partial derivative of c at spatial point 0 with respect to the spatial dimension. And then we've got another system, dc of delta x comma t, dt is d times the second partial derivative of c at delta x and t with respect to x and so forth. So we've got something that's sort of like when we had multiple dependent variables. We're kind of considering evolution of a set of individual points, and you can almost think of them in the same way. So just as we handled this in the case of multiple dependent variables, we could sort of say there's a separate variable for each spatial point, and then just kind of handle them in sequence each time step as we go through our simulation. But that doesn't quite work, and we'll need to see why it doesn't quite work and what we do about that. So to see how to do that, let me just introduce some notation here. So I'm going to refer to x sub I as the ith spatial point. So in other words, I times delta x, if we're assuming we start at a spatial point 0. And then what we're going to say is that the notation c sub j of x sub I is going to mean the value of the function, at least an approximation of it, at spatial point I delta x and time point j delta t. So this is going to be our general notation for what we're trying to solve here, and then we're going to be trying to solve that for all spatial points I and all time points j over whatever regions are of interest to us. And then we can sort of say, just as we did with the previous problems, that we can come up with a scheme for integrating over j that's going to look something like the following. So we could say that for any time point n, we can derive time point n plus 1 at spatial point xi by, let's say, the value at time point n and spatial point xi plus delta t times the partial derivative at time point n and xi with respect to t. So this is just a statement of the forward Euler method at this particular point. And that's going to be equal to c sub n xi plus delta t times the second partial derivative of c sub n at xi with respect to x. So in some sense, what we'll be doing to integrate these kinds of systems is just using this iterator just like before, so just a forward Euler, leapfrog, or whatever other scheme we wanted to use. But there's still one problem here, one reason we can't quite use that. Does anyone see what that is? What problem would you run into if you tried to code up a numerical integrator using this iterator? Well, if we're treating this as a set of independent variables, a set of isolated points in space, then the derivative with respect to space doesn't mean anything. You can't have a derivative with respect to space of a single point in space. So we need to do something to figure out what these second derivatives are, or at least to get an approximation for them. And we can do that very much the same way we got approximations for derivatives with respect to time. So that is, use finite difference methods. So use the differences between nearby spatial points to get an estimate of what the spatial derivatives are at those points. So there's a general formula we can use to get an estimate of a second derivative, and it looks very similar to some of the formulas we've seen before for numerical derivative estimates. So in general, if you've got some function f, then the second partial derivative of f with respect to some dimension x is going to be approximated by f of x plus some delta x plus f of x minus delta x minus 2 f of x over delta x squared. So this is known as a centered difference approximation. And that's something we could plug into our formula here if we want to get an approximation of the second derivative with respect to space based on our discretized spatial coordinates. But before we see how that works, I do want to analyze this approximation so we can see why it works and how well it works. And we can analyze this very similarly to how we've analyzed other derivative approximations. Basically, what we're doing here is a linear combination of a few different perturbations of f of x. And the usual way we would try to make these comparable to one another is to do Taylor expansions of the approximations. So, for example, we can say f of x plus delta x is going to be given by the Taylor expansion, f of x plus delta x f prime of x plus delta x squared over 2 f double prime of x plus delta x cubed over 3 factorial f triple prime of x plus, I'll truncate it there, at some order delta x to the fourth term. And similarly, f of x minus delta x is going to be f of x minus delta x f prime of x plus delta x squared over 2 f double prime of x minus delta x cubed over 3 factorial f triple prime of x plus another order delta x to the fourth term. And then the third thing we have here, f of x is just f of x. And what we're trying to say in this formula is that basically in the numerator at least, we're taking the first thing here plus the second minus twice the first. And if we work through the math of all of that, what's going to happen is the f of x terms cancel out. We've got f of x plus f of x minus 2 times f of x. We're adding a plus delta x f prime of x to minus delta x f prime of x, so that cancels out. These two are going to add together, so we're going to get delta x squared f double prime of x. These two will cancel out. These two will add together. So we get order delta x to the fourth. And then what we can basically say is, if we take the left-hand side here and the right-hand side, divide through by delta x squared, what we end up concluding is f of x plus delta x plus f of x minus delta x minus 2f of x over delta x squared is this divided by delta x squared, which is f double prime of x, plus this divided by delta x squared, which is order delta x squared. So what that's telling us is that this whole thing is an approximation to the second derivative with respect to x, and in particular it's an approximation with an error that's proportional to delta x squared. So does that make sense to everyone? Okay, well that is basically giving us what we need to make a numerical integration scheme that can deal with these second derivative terms. In particular, what we can do is simply plug that formula into the thing we are trying to do here, so make a forward Euler iterator. And what we're going to end up with is the following. C sub n plus 1 of xi, so that's our approximation to the ith spatial point at time step n plus 1, is given by C sub n at xi plus delta t times the diffusion constant times this approximation scheme, which will come out to C sub n at xi plus 1. So nth time point I plus first spatial point plus C sub n x sub I minus 1 minus 2c sub n xi over delta x squared. And this then is giving us an iterator for a forward Euler approximation using the second order spatial derivative approximation. Very often when we're working with these kinds of schemes, we'll want to rewrite a bit. So move this thing to the left-hand side and divide through by delta t to get this in the following form. C sub n plus 1 xi minus C sub n xi over delta t is equal to d times Cn xi plus 1 plus Cn xi minus 1 minus 2 Cn xi over delta x squared. And the reason we write it in this form so that there is a time approximation on one side and a spatial approximation on the other is that we can use the fact that this is a first order forward difference approximation to the time dimension. So we know this is an approximation to dc dt with error order delta t, and this is an approximation to d squared c dx squared with order delta x squared error. So just writing them this way lets you think about this in terms of approximations to two derivatives. So any questions at this point? All right, so one of the reasons to write it this way is that very often you want to think about what kinds of approximations you're making with your schemes, and particularly the orders of errors of those approximations. Because if you want this to work efficiently, it's not enough just to pick an appropriate delta x and an appropriate delta t. You also want to pick those to be appropriate to each other. And what I mean by that is that you want these two error terms to be roughly comparable to each other. So if you had a delta t that's much smaller than delta x squared, then what that basically means is that you're wasting effort taking very small time steps because the error in your spatial approximation is just going to overwhelm the error in the time approximation. You could make your step size bigger and really not lose any accuracy. And conversely, if delta x squared was much smaller than delta t, that would be wasting work on each of your spatial approximation, because you're accumulating so much error on each time step, it's just killing all the advantage you get from having a small spatial step. So basically, more or less, you want delta t to be proportional to delta x squared for a scheme like this. Any questions about that? Yeah?
I think I missed something. Why did we stop the Taylor expansion at order 4?
Well, we could have kept writing. I stopped it at order 4 because I knew that that's how far you would need before the terms wouldn't cancel out. So basically, if you're doing a proof like this, you want your approximation to go at least as far as the first term that doesn't cancel out beyond the thing you're actually trying to approximate. So here, it matters that the third order term cancels out and the fourth order doesn't, so you need enough terms to show that. Any other questions? All right, so we can do something like this and pretty much combine whatever kinds of temporal and spatial approximations we want to come up with different schemes for numerical integration. So if, for example, instead of a forward Euler approximation, we wanted to use, let's say, a leapfrog approximation to get a more accurate scheme here, we could say that the leapfrog would be given by c sub n plus 1 at xi is given by c sub n, or excuse me, c sub n minus 1 at xi plus 2 delta t times our approximation to the derivative at time step n in position xi, which then would be our spatial approximation, c sub n xi plus 1 plus c sub n xi minus 1 minus 2 c sub n xi over delta x squared. And this then would give us a leapfrog iterator where we would now have second order accuracy in time and second order accuracy in space. And just as I did with the forward Euler iterator, we can rewrite this and move this to the left-hand side, get c sub n xi minus cn plus 1 xi minus cn minus 1 xi over 2 delta t is equal to, I guess I left out a d here, diffusion constant times cn xi plus 1 plus cn xi minus 1 minus 2cn xi over delta x squared. And then what we have here is an approximation to the second derivative with respect to space, so d squared c dx squared plus an order delta x squared error term. And you can probably guess that this thing is an approximation then to dc dt plus an order delta t squared error term. So if we did this scheme, which is now leapfrog in space and the second order, or leapfrog in time and the second order center difference in space, then we would probably want delta t and delta x to be roughly comparable to get the error terms to balance. Any questions about any of that? All right, so we have a couple more issues we need to worry about before we can actually get a numerical integration scheme out of this. So this pretty much is giving you the heart of a numerical integrator for a system like this. And this line here is basically the thing that would be in the central loop of a program doing numerical integration for this system. But there are a few complications we need to worry about to actually get a useful version of this where you can actually get a program to implement the system. One of these is what's called the initial conditions. And the initial conditions are something you have to worry about in writing a program to do this, although usually it's not a complicated issue. It just means that whereas with a let's say a function just x of t, we would have to have a single value of x. We have to know x of 0. Now when we've got a function c of x and t, we need to know c of x and 0 for every spatial point x. So that's basically what we mean by initial conditions, and usually this is something you would figure out based on the problem you're trying to solve. So if you were looking at that capillary version of the diffusion problem, then we would set it up so that for all of the points here, we've got some C of xi comma 0. We maybe set those to concentration 1, and all of the points here, C of xj comma 0, maybe be set to 0, and that would be setting up the initial conditions. You just run through, set the value of C at every spatial point at time point 0. Does that make sense to everyone? All right, so that's kind of the easier thing we need to worry about. But then we get to the harder one, and that's something called the boundary conditions. So boundary conditions are something we can illustrate by looking at what would happen if we tried to run just that basic iterator in our capillary example. So we've got a set of spatial points. And when we're doing our second derivative approximation, if we were trying to figure out the approximate to the second derivative here at time point n, then we look at this value, and we look at this value, and we look at this value, and we get an estimated second derivative. But the problem comes in if we try to figure out what the second derivative is here. So we look at this value, and we look at this value, but there's no value here. So that's what we mean by boundary conditions. We have to do something special, or no matter how you set this up, you're always going to have something that runs off the end of your boundaries, whatever boundaries you have. Now there are different ways of handling that. So one of the easy ones might be, we just imagine that we wrap this around into a tube, and then you would have to have a special condition that says, if you try to pick spatial point -1, you wrap around here, and vice versa. But usually if we're looking at a physical system, we need to do something a little more complicated than that. And what you do depends on your assumptions about the problem. So different models we would want to pick will lead to different boundary conditions. The easiest version of this would be to assume, let's say we've got these capillaries, and we just assume we've got a big volume of solution at each end. So maybe this volume has high concentration, and this one has low concentration. And then we could just say that effectively, to the left of this tube, we have a fixed concentration, C0, which is equal to 1. And to the right of the tube, we've got a fixed concentration, C1, which is equal to 0. And then we would just have to know when we get to running through this step of our iteration, and we're looking at I equals 0, then we just have to know that, that to the left of the tube, we plug in the value of 1 wherever that comes up. And we know if we're at the right end point of the tube, then we just pretend the thing to the right has the value 0 plugged in whenever it comes up. So that's pretty straightforward. You just test boundary, and then basically everything will kind of work to simulate that model. That also works if we were assuming there is some function of time that describes what's happening here. So maybe we want to assume that this big volume is being diluted over time, so at any given time point it has some concentration e to the minus lambda n delta t. That also still works. You can just say that whenever you need to figure out what this is, you look up what time step you're in, you compute the value of this, and you plug in that value for the kind of virtual point to the left of your tube, and then that also is going to work and will give you a correct simulation of what would happen if you had this time-varying concentration off to the left. Does that make sense to everyone? All right, so these collectively are known as Dirichlet boundary conditions, and they're kind of the easy case. You just need to know what concentration you're asserting is off to the sides of your boundaries, and then plug that in when you come up to that condition in your code. The more complicated situation is that sometimes the boundary condition we want to set is an assertion about the derivative of the concentration rather than the concentration itself. And those are known as Neumann boundary conditions. And an example of this would come about if we do something that would seem pretty natural in these kinds of situations. Let's say we've got our diffusion example with our tube, and we're just going to assert that we cap off the ends of the tube. So that ends up being something we would model by a constraint on the derivatives. In particular, what we're asserting if we put a cap on the end of the tube is that dc dx is equal to 0 at that left endpoint or at the right endpoint. So in other words, what we're saying is if the tube is capped, then there's no flux of concentration across the end, and that's exactly what this is saying. There's no spatial change past the end of the tube, and so we get a constraint like that. So that ends up being a problem for us because our formula for approximating the second derivative, which is the thing we need to know about, depends on knowing the value of the concentration. It doesn't use the value of the derivative, the first derivative, it uses the value of the concentration. And with a constraint like this, we don't have that. So can anyone think of anything we might do in that case? Well, basically what we end up needing to do is, when you get to these boundaries, if you've got a derivative constraint like this, you just need to use a different formula. So you have to figure out a different formula that uses dc dx rather than c to estimate the second derivative. And we can kind of see how to do that by looking at the following. Let's say we are trying to figure out the value of c at the left end point of this tube, and we have this constraint that dc dx is equal to 0 there. Well, in the normal approximation, we would use the value of c at point 0, which we know, and we would use the value of c at point delta x, which we know. And normally we would use the value of c at point minus delta x, but we don't have that. But we do have the derivative of c at point 0, because we've got the assertion that that's 0. So what we want to do then is come up with an approximation that depends on these three things. And what we can say is, if we put these together, then let me rewrite this a bit. Let's say we've got c of delta x, c of 0, c prime of 0. And what we would want to do is come up with some formula that lets us combine these things, just like we combined c of delta x, c of 0, and c of minus delta x. Or in other words, take a linear combination of these and find the right combination so we get an approximation to the second derivative. So just as with the normal spatial derivative approximation we used, we can figure out the right approximation by using a Taylor expansion. So we're trying to figure out the second derivative at point 0, so we can expand this, and we can say that this is c of 0 plus delta x, c prime of 0 plus delta x squared over 2, c double prime of 0, and then I'll truncate it with an order delta x cubed term. We can say that this is just c of 0, and we can say that this is just c prime of 0. And then what we want to do is find some scaling factors on a, b, and c, such that a times this plus b times this plus c times this is the thing we're trying to figure out, which is d squared c dx squared at 0. So how would we do that? Well, it's basically just a linear system. So for that to be true, it has to be true that a times c of 0 plus b times c of 0 is equal to 0, so these have to cancel out. So we get the assertion a plus b equals 0 for these two things to cancel out. We want the c prime terms to cancel out, so we get the assertion that delta x times a plus c has to be equal to 0 to cancel out the C prime term. We don't want to cancel out the C double prime term because that's the thing we're trying to figure out. So we want the assertion that A times delta x squared over 2 is equal to 1, so we get exactly C double prime of 0. And then ideally we would want to keep going and cancel out more terms after this. The more terms we can cancel out after this one, the more accurate this will be. But for here, we've now got 3 equations and 3 unknowns, so that's as far as we're going to be able to get. So we can solve for the different terms here. This is going to imply that A is equal to 2 over delta x squared. We can then solve C using this term. We're going to get C equals minus delta xa. This one's going to imply that B equals minus A. And if we put all of that together, what we're going to end up concluding is that we can approximate the second derivative of x, or C with respect to x with the following formula. D squared C dx squared at spatial point 0 is going to be approximated by 2 over delta x squared C of delta x minus 2 over delta x squared C of 0 minus 2 over delta x C prime of 0. Or in other words, the approximation formula we want is going to be that this at point 0 is approximated by 2c of our iterate x1 minus 2c of the iterate x0 minus 2 over delta x C prime of 0, all divided by the delta x squared. Now our boundary condition asserted that dc dx at 0 is 0, so we can kind of cancel out that term. And what we end up with is a special formula, 2c x1 minus 2c x of 0 over delta x squared. And then we simply plug that in place of this thing when we're at the left boundary, and then we get an approximation that enforces this derivative condition on the boundary. Does that make sense to everyone? Okay. So can anyone tell me what order of accuracy that approximation is? We can figure out the order of accuracy by looking at how we derived this. So we had picked A, B, and C, so that we cancel out these terms, we cancel out these terms, we don't cancel out this one, and since we've just got this order delta x cubed term left in from A, basically that's going to be the error term, except that we then divide through by delta x squared over 2 to make this exactly C double prime of x. So basically the error is going to be delta x cubed divided by delta x squared, or delta x. So this is going to be an approximation to d squared c dx squared at 0 with an error term that is order delta x. Now, since we're usually using second derivatives approximations that have an error term of the form delta x squared, this probably isn't what we're going to want for our approximation, because the error we're introducing at the boundary is then going to overwhelm the usual error of our scheme. It's kind of ruining the scheme to throw in this order delta x error. So probably what we would really want to do is come up with a better approximation that has an order delta x squared error term like the rest of our scheme. Can anyone think of how we might do that? If we wanted to use this derivative constraint to get a second order approximation, what are the steps we would work through to do that? Well, it's basically more or less the same thing as what I derived here. We need to combine a few values we do know and find the right linear coefficients to make an approximation formula. So if we want to cancel out more terms here, so cancel out this delta x cubed term, we're going to have to throw something else into the mix. And the most obvious thing to do would be to throw in, let's say, one more term. So throw in a d c of 2 delta x, to take the next point inward, and then solve for a, b, c, and d to cancel out this, and cancel out the delta x cubed term, and then we'd be left with a delta x to the 4th term. When we divide through by delta x squared, we get a second order scheme. So any questions about this? Okay, so that basically then is giving us more or less what we would want to, if we want to put together a full method for solving this kind of numerical integration of a diffusion problem. Pretty much at this point you have all the things you would need to put together a real piece of code that would do this. The basic iterator we had is the main thing that would be in the central loop, but then we would need some initialization where we program in our initial conditions, and then each time you run through, whenever you're at a boundary, so the endpoints of the capillary, you plug in whatever boundary scheme you have, whether it's Dirichlet or Neumann, you plug in that boundary scheme, and then you get a piece of code that would simulate the diffusion within that capillary. And so it's pretty easy to generalize that to multiple dimensions. It gets kind of messy to write, but if we went back to the original problem where we were looking at diffusion in a 3D system, we would have dc dt is d times d squared c dx squared plus d squared c dy squared plus d squared c dz squared. And we can just use the same spatial approximation to these second derivatives for each of those terms here. So we can say that c sub n plus 1, now at the spatial point xi, yj, zk, is given by c sub n at xi, yj, zk, plus delta t times the approximation to the derivative at time point n and spatial point xi, yj, zk, and that is given by the spatial approximation d times, first of all, the approximation to d squared c dx squared, which now becomes c sub n xi plus 1 yj zk plus c sub n xi minus 1 yj zk minus 2 c sub n xi yj zk over delta x squared. So that is the approximation to this thing. And then we have an analogous term for y. That's c sub n xi yj plus 1 zk plus c sub n xi yj minus 1 zk minus 2 c sub n xi yj zk over delta y squared, and then finally cn xi yj zk plus 1 plus cn xi yj zk minus 1 minus 2cn xi yj zk all over delta z squared. And this then would give us a numerical integrator, at least the core piece of code for a numerical integrator for integrating a 3-dimensional diffusion problem. So at any given time point n, when we're trying to figure out the value at time point n plus 1, basically what you would need to do is just wrap this in a few for loops. So for I gets 0 to whatever, 0 to k, for j gets 0 to k, for I guess I should have picked something else here. So let's make that an m. Where k gets 0 to m. And basically, that is giving us most of a numerical integrator for solving this diffusion problem. So at time step n, we're trying to run through the value at time step n plus 1 for every spatial point I, j, k. And then the entire right-hand side here only depends on values at time step n. So we're able to run through all of the values at step n to figure out values at step n plus 1 and so forth. If we actually wanted to implement that, of course, we would need to worry about now initial conditions for the three-dimensional space. We need to set that for every value of ijk at time 0, or step 0, n equals 0. And we need to worry about boundary conditions in 3 dimensions. And in 3 dimensions, of course, your boundary conditions could get quite a bit more complicated. So we might have boundary conditions where we have to sort of have special handling for each surface, maybe other handling for each edge, and other handling for each corner. And you can always imagine that maybe you are simulating a space that's sealed on some surfaces and kind of feeds into some big volume on other surfaces. So it can get pretty involved, but basically this line here is the core of a numerical integrator for this problem. So any questions about that? All right, so just as before, it would be pretty easy to use a different time scheme. So if we wanted to turn this into a leapfrog iterator, all we would need to do is make this c sub n minus 1 and make this 2 delta t. We now have a leapfrog integrator for the same system. There would be second order error in time and second order in space. But basically that's kind of the core of how these things work. So any questions at this point? All right, so that's giving us numerical integration for diffusion systems. But of course, there would be a lot of things we might be interested in simulating other than diffusion. But the basic ideas actually apply pretty broadly to things we might want to simulate when we're looking at multiple independent variables. And we can see how you can generalize this by considering a typical kind of thing we might want to simulate. And that is what would happen if we maybe take that problem we've been looking at already. So box where we have concentration here, a concentration here, remove the boundary and let things diffuse. But instead of assuming it's just concentration of some chemical here at high concentration, low concentration here, let's assume instead we've got one chemical here, a different chemical here, and those two chemicals react with one another. So maybe we'll assume they go to some product with some rate K1, K2, and we want to simulate this system. So we want to know what happens if we pull out the boundary between these and they start diffusing and reacting with one another. We'd like to be able to simulate, as a function of time, how are A, B, and P distributed in this space. Right, so the way we would do this is using an extension of what we just saw that is known as a reaction diffusion equation. And it relies on the fact that because derivation is a linear operator, you can basically just add different contributions to a derivative and you'll get the right answer. So in other words, if the amount of A at a given point in space is changing because of diffusions, it's diffusing away to neighboring points, and it's changing because of reactions that are consuming A because it's reacting with B, you can just add the... So in other words, what we can say is that dc dt, where here I'm referring to C as a vector that has components A, B, and P, would be given by the contribution of diffusion to that. So these diffusion effects, the Laplacian operations, plus a contribution I'll call f of C to the reactions, or contribution from the reactions in the systems. And this f of C is just what I've already referred to in the last class as the law of mass action equation. So how at any instantaneous point in time, A, B, and P are evolving through reactions from one another. So in other words, we would get the system, partial A with respect to T is equal to d sub A times the Laplacian operator, d squared A dx squared, plus d squared A dy squared, plus d squared A dz squared, plus a contribution from the law of mass action reaction equations, which says that at any given spatial point, the way we lose A is by combining A and B to produce P with a rate K1, and the rate at which we gain A is P breaking down with rate K2 into A, or in other words, we gain A at rate K2P, and we lose A at rate K1AB. So that is our first reaction diffusion equation. And we can say the same thing with respect to B. So dP dt is some diffusion constant for B times the Laplacian with respect to B. So dB squared dx squared plus d squared B dy squared plus d squared B dz squared plus the same reaction term. So we gain B at rate K2P, we lose it at rate K1AB. And finally, dP dt is diffusion rate of P times Laplacian P, dP squared dx squared plus d squared P dy squared plus d squared P dz squared plus the rate at which we gain P, which is K1AB, minus the rate at which we lose P, which is K2P. Everyone follow that? All right, so if we actually want to make a numerical integrator for that, it's not too different than what I've shown here. So we pretty much would just need to add the diffusion terms from a numerical integrator to the reaction terms, and we already know how to do both of those things. So basically, the core of an integrator would look like the following. At each cycle through our integration, so each time step n+1 that we're trying to solve for, we would have to figure out the value of A at step n+1 at each spatial point xi, yj, zk. And if we were doing, let's say, a leapfrog iterator, then we would say that that is an-1 at xi, yj, zk plus 2 delta t times the numerical approximations to these derivative terms. So that would be 2 delta t times first the diffusion term, d sub a, and then we use the numerical approximation to the diffusion, which we know is a sub n at xi plus 1, yj, zk, minus a sub n at xi minus 1, yj, zk, minus 2 times a sub n at xi, yj, zk over delta x squared. So that's numerical approximation to this term. And likewise, we would do the same thing with respect to the y and z dimensions. So a sub n xi, yj plus 1 zk minus a n xi, yj minus 1 zk minus 2an xi, yj, zk over delta y squared and an xi, yj, zk plus 1 minus an xi, yj, zk minus 1 minus 2an xi, yj, zk over delta z squared. That's giving us our numerical approximation to the Laplacian. And then we just have to additively put in the contribution from the reactions. So we would also have a term 2 delta t times the value of the reaction at time point n and spatial point xi, yj, zk, which is going to be given by, exactly as in our ordinary differential equations, K2 times P at time point n and spatial point xi, yj, zk, minus K1, A at time point n, xi, yj, zk, times B at step n, and constant point xi, yj, zk. So that whole thing gives us a numerical integrator to figure out the value of A at time point n+1 in each spatial point, xi, yj, zk, using values at prior time points, so n and n minus 1. So that would be a leapfrog iterator. And we would basically do the same thing with respect to the other two variables. So v sub n plus 1, we would figure out at xi, yj, zk. I'm not going to bother writing the whole formula, but basically it's the same thing. We would say use v sub n at xi, yj, zk, and then we would add in 2 delta t times the approximation to the derivative, so an approximation of the Laplacian term using the b sub n values, so xi plus 1, yj, zk, and so forth, plus, b here, plus an approximation to the reaction term, 2 delta t times k2 pn xi, yj, zk minus k1 an xi, yj, zk pn xi, yj, zk, and likewise the same thing for p, so p sub n plus 1, we would figure out at xi, yj, zk, given p sub n minus 1 at xi, yj, zk, plus 2 delta t times the Laplacian for that, which I'm not going to bother writing, plus the reaction term, 2 delta t times, in this case, minus k2 pn at that spatial point, plus k1 an at that point, bn at that point. So does that make sense to everyone? Right, so just as with the pure diffusion problem, we have to worry about things like initial conditions and boundary conditions. But basically, you take these 3 equations here, fill in all the parts I didn't bother writing, wrap them in 3 for loops, and you've pretty much got your simulator for this kind of system. You have to throw in all the special checks when you hit the, I equals 0, or I equals m, or j equals 0, and so forth. But basically, that's the heart of a simulator for this. All right, any questions about any of that? And so, there are other sorts of situations where we might want to use the same kind of technique. So another place we have to worry about these kinds of partial derivatives is in a process called convection. And convection just means if we've got, let's say, some chemical that is moving along a gradient. So instead of thinking of it kind of passively diffusing, imagine it's actively moving. So if we were, for example, studying a chemical that is simply flowing at some fixed rate, that would be described by, let's say, a system like this, dc dt equals minus dc dx. That's what you would get if you had a spatial system in which we had some pattern of chemical gradient and we're simply moving in the plus x direction. This partial differential equation describes the behavior. And more generally, we can say dc dt is minus v sub x dc dx minus v sub y dc dy minus v sub z dc dz would give a description of a chemical and a gradient in a 3-dimensional space that is moving along the vector vx, vy, vz. And this is another kind of system we could simulate with the same sorts of ideas. So let's say we want to set up a forward Euler integrator for this system. We could say that c sub n plus 1 at spatial point xi, yj, zk, and I'll write this in the shorthand I used before, that minus c sub n at xi, yj, zk divided by delta t, this is the statement of what the forward Euler iterator is telling us, is equal to a numerical approximation of this thing. And how would we numerically approximate this thing? Let's start with the first term here, v minus v sub x dc dx. How could we approximate that? Well, we already know a formula for approximating first derivatives, so that's exactly what this does. So we could say that this is equal to minus b sub x times, now we want a first derivative approximation with respect to x, so we would say c sub n xi plus 1 yj zk minus c sub n xi yj zk over delta x, and that's a numerical approximation for this thing. And likewise, minus by cn xi yj plus 1 zk minus cn xi yj zk over delta y, which is an approximation to this term, and minus v sub z, cn xi yj zk plus 1 minus cn xi yj zk over delta z. And then this thing is basically the heart of a numerical integrator for this convection equation. So if we actually wanted to implement this, you would multiply through by delta t, move this to the right-hand side, and then we've got something that gives us the value at time step n plus 1, spatial point ijk, given values at time step n. Does that make sense to everyone? Suppose we wanted a more accurate scheme. So let's say instead of doing a forward Euler method, we wanted to do a leapfrog method. So I plug in, let's say, the leapfrog iterator here. So this now becomes c sub n minus 1, and this becomes 2 delta t. And now this is describing a leapfrog numerical integration scheme. That will create a problem here if we don't make some adjustments. So what problem is that creating? Well, basically, we've changed the order of this scheme, so that is now an order delta t squared error for that scheme. So we would probably want to adjust our delta x, delta y, and delta z to make them work correctly so that these are in balance. You want the order delta x or delta y or delta z errors on the right-hand side to be about balanced with the order delta t squared errors on the left-hand side. Suppose we wanted to solve what is called convection diffusion equation, which means we have an equation dc dt is equal to, let's say, a Laplacian of c plus dc dx. We already know some numerical approximations for the Laplacians. We can throw these in here. And we know some numerical approximations for the convection term. So let's say we use this approximation for the Laplacian and this approximation for the convection term. That's also, I will claim, going to create a problem. What problem will that create? Well, that creates a problem because this is a second order approximation. So this has error order delta x squared, but this has error order delta x. And you don't want to have a delta x error mixed with a delta x squared error, because then the error of this is going to kind of ruin the accuracy of that other approximation. So what can we do about that? What we would probably want to do is replace this for the second order accurate approximation. What would be a second order accurate approximation we could plug in here? I'm going to claim we already know how to do a second order accurate approximation of the first derivative. Well, that's exactly what the leapfrog scheme is. So this is a second order accurate approximation of the first derivative, and we can use the same thing here. We could plug in the approximation c sub n of xi plus 1 yj zk minus c sub n of xi minus 1 yj zk over 2 delta x. That's a second order approximation to dc dx. Does that make sense to everyone? All right, so you can get a lot more sophisticated with these kinds of things. You can have convection diffusion equations, you can have convection reaction equations, convection reaction diffusion equations. So basically, because all these terms act additively on the derivative, you can just throw in a diffusion term and a convection term and a reaction term, and it's all basically the same ideas. You pretty much come down to using some numerical approximations to your spatial derivatives on the right-hand side, numerical approximation to your time derivative on the left-hand side, put it all together, and you get a numerical integration scheme for your partial differential equations. So does that make sense to everyone? Okay, so there are a lot of other things we can learn about this, and I'm basically spending this one lecture on this topic, but you can take whole courses. I think there's at least a sequence of 2 courses you can take here on numerical integration of partial differential equations. So there's a lot more detail you can learn about good schemes for particular systems, or how to get good stability properties for particular kinds of systems, or particular ways of combining this. There's a lot more theory, but this gives you some basic tools you can use that will pretty much get you an acceptable solution to almost any kind of problem of this kind.